Now the issue is that these detectors turn the radiation into light and then measure that light. But if we have all kinds of light in the room coming from the ceiling and everywhere else, how do we get rid of all that light and noise? The answer is we use one of these babies. This is a dark box, and we can open it up, and inside here we can stick our detector that we are testing, connect the cables on this side, which come out this side, and then we can close it back up, lock it up, and then do our experiment in here. So I have our coupled assembly here, which I'm going to carefully place inside the dark box. And as you can see, I have connected the proper cables. Red is for high voltage, and green is for the data coming out of the detector. So let's close it up. And if we set this to the proper voltage polarity, power up, we already see some pulses coming in even though we don't have a radioactive source. And that's because on Earth, we always have cosmic ray radiation showering down on us at all times. Nothing to worry about. Now, if I add a radioactive source near the detector, we should see much faster counts, which we sort of do. So now what I want to do is take just one of these mini pulses that we're getting, freeze it in time, and then zoom into it and take away the information that I want to get from it. You can do that like this. So after doing that, you can see that this pulse is roughly 1, 2, 3, 4, 5, 6, 7 maybe blocks long before it returns back to its 0 point, and roughly 1, 2, 3, 4, 5 blocks high. And if we read here, this is 200 millivolts per division and 10 microseconds per division. So if we do the math of how many blocks wide and how many blocks tall this pulse is, we can figure out the voltage, which represents the energy of this pulse, and we can figure out the time that it took this pulse to go up and then come back down. So now I can repeat the entire experiment for the other detector, and we'll see if there's any difference.